do you know? Yeah, we do know how an engine works. Yes, yes. Okay. So we have like the three main like ways, like, so we use these models kind of to approximate or idealize how an engine works, because that way we can actually calculate things. So yeah, as you should be familiar with, let me go get my, should have height and medium controls and stuff. Stuff is annoying. Okay, so you already know kind of that, like you have like a bit of a cycle thingy, and then you have like a little cylinder that moves like up and down. And then like, so your first stage was, it's going to be intake, where it comes down. So you have like intake, and then like the thingy comes down. That's like number one. And then like number two kind of has compression, where it goes up. So you could, some people call this the combustion stroke, other people call it the power stroke. No one cares what it really is. We get the idea. So combustion. And then there's the exhaust. This is like for a 4-stroke. For a 2-stroke, it's like you do, it's kind of like the middle two kind of go together, and then the other two kind of go together, quote unquote, sort of. I might be wrong on that, but that's kind of the general idea. And then combustion, and then there's exhaust. Yeah, okay. So the idea is that these 4 steps get idealized. So in a real like cycle, how does a real one look like? I've got how it looked like somewhere in my notes. One sec, sorry. Where did it go? Okay, I guess it disappeared somewhere. Yeah. Not that. Oh, there it is. Yes. Found it. Okay, cool. So it's like normally, sorry, not the TS diagram, the PV diagram, pressure volume. So you can imagine when you're in your intake stage, you start up at a very low pressure or atmospheric pressure, at a low volume, at a large volume, so big volume, low pressure. And then what happens is when you compress it, you go and you convert that into a higher pressure, but with less volume. And then you combust the fuel. And so what happens is, as you combust it, you add pressure because you're burning stuff, and then it kind of like decreases. It decreases the pressure to some value, and then you exhaust, which takes you back down, or something like that. So it's like, so the way it kind of looks like is it comes around like this, and then it kind of like goes up around like that. So the idea is that it's like a weird way. So it goes over to here. This is exhaust. This line that I just drew now, that's exhaust. This across around here is intake. And then this is compression, this line over here. This is compression. And then this is like combustion. Combustion actually happens like the whole cycle, because it's like it pushes all the way down.
Wait, is that part, could you say that's expansion as well?
Or expansion, yeah. Combustion, expansion, yes.
Okay, cool.
Same thing, yeah. So that's the idea. So like what you're taking is you take regular air. So you start up from the top. So you start from a low volume. You go down, suck in a lot of air, but it stays about the same pressure, more or less. And then you compress it, so it comes up this cycle. It's like a figure-8 loop, but it's like a really distorted. So yeah, then you press it all together, and by pressing it, and it's in a sealed container, so then it increases pressure and decreases volume. And then once you burn fuel and stuff, then yeah, you add pressure, stuff burns. And then you have some hot gases that's moving down, that pushes it down. But then when it comes all the way down, you still have hot gases. And then so you kind of push it back up, and you're pushing out those hot gases. So that's why there's a bit of an energy loss here, because there's a bit of hot gases that you're not actually using that energy. So this is actually a bit of a waste here. But the thing is, what we really do in like our idealizations is we only really focus about this, and we assume that our losses are negligible. Does that make sense?
Yeah.
So like in exhaust, you've burned gases and your air is still pretty hot. Like, you know, if you feel the exhaust of a car and motorcycle and stuff, the air is still pretty hot. But that heat's kind of getting rejected and wasted. So that wastage is the little bit on the bottom, but you don't really account for that. So the focus of our cycles is really just the top bit, where the energy is actually like quote unquote being used to like produce work. Cool? Yeah. Okay.
Yeah.
So this is the real cycle, like straight up real. Now from here, we want to like idealize these with all sorts of ways. So the first way that we think about things is an Otto cycle. The Otto cycle does things. So instead of this, what you can imagine is, so that's the PV diagram. There's Otto. The diagram that I got is a TS diagram, which is kind of annoying to work with. I can guess what the PV diagram would be. It would be like kind of like this, but not really. So you can imagine, so when you go from here to here, you have a constant volume of gas, not constant volume of gas, but like it's a there was a word for it. Isentropic. That's right. It's an isentropic compression. So what happens is S is equal to constant over here. And then what happens is you do a heat addition. So isentropic compression, V equals constant heat addition. And then from there, you have your expansion, which is also another isentropic expansion. And then you exhaust, which is now, yeah, so if you want me to label this is your expansion part. So that sorry, this is compression. That's number 2. This is number 3, idealized. And then this is still number 3. It's like combustion and then expansion. That's still 3. And then this is your exhaust, where you drop your heat. Yeah, sorry. Does that sort of make sense? Yes, no?
Yep.
Yeah, same stuff from above. The thing is, every time you do cycle analysis, you always need something to be the same. Like at every stage of something needs to stay the same so you can compare values to each other. It's like you're working off like a link. And so when you work off a link, at least every part of the chain, you have like at every point, either you're at an intersection of a link or you're on the same like link itself, if that's what I mean. Makes sense. So it's like from this point to this point, S is constant. From this point to this point, V is constant. And then from this point to this point, S is constant again, and downwards V is constant again. So the idea is that like you always have something constant. It may be changing each step sort of, but the thing is like in each step, you can use that constant value to like work things through. That makes sense.
Yeah.
So 2 things that you actually really do need to know though, are like fundamental things, is you need to know what this volume is and what this volume is. There's words for those. I forgot what it was. All right, top TDC and BDC, if you know what those are. I don't know. TD, top down center or something, and then bottom down center. So this is like your maximum volume and minimum volume. That makes sense. It's literally like the maximum volume of gas that you have in the cylinder and then minimum volume. Yay, nay?
Yeah.
Yep.
Yeah, so you can work that out through your stroke and stuff. But once you know those 2 volumes, then you can actually work things through. So the way that you're kind of like trying to work things through, you start up at a known condition, likely this point. At this point, you are at the bottom and you're at atmospheric pressure. Right, so at this point, I'll call this point A. I don't know, I'll just call this A, B, C, D. So that way we don't get things confused, hopefully, maybe, I don't know. But yeah, so at point A, so that's atmospheric pressure. Well, it makes sense to me to make it atmospheric. Pretty sure it is, but might be wrong on that. Yeah, atmospheric pressure. And then this is like your maximum volume. That's BBC. At this point, yeah, your cylinders, like the piston thingies at the bottom. Anyway, so that's point A. And then from there, you go from point A to point B. And so what you are meant to do is, at every point, you want to know the entropy, the S, and the volume, because those are the main things you're dealing with here, entropy and volume. But it's a good idea to know the pressure as well. So this is kind of like the state of the system, if you've heard that before. So what you're really looking for is, so at all times, well, this is red, yeah, at all times, you want to know. You want to know S, you want to know pressure, and you want to know volume. The volume is kind of given to you because you know the volumes of those two times. So the volume is kind of already known. So you kind of already know that, but the pressure is not necessarily obvious. You may want to work that through, and same with S. So what you are meant to do is, you know that S stays the same at this point. So from here at point A, you want to calculate what S is. That's your entropy at that point, like your lowercase s or uppercase s, depending. But I think it's just the lowercase that you work with. So yeah, you just calculate what this value is. Then when you compress, so what happens is you have S for a particular volume. You can use that same S for a different volume, and then you can calculate the pressure out of that. Did that make sense?
Yeah.
Right, so you can imagine this as S1 or SA for our case. Don't actually use the same notation as me, otherwise the guy will probably be like, what is this notation? Yeah, so you can use SA with your TDC volume. With these two pieces of information, you can solve for pressure, which is your pressure at B. That pressure over here. Does this make sense?
Yeah.
Okay. So that's basically all you need to know. Remember, at all times, you know S, B, and P. So you know that SB is the same as SA because it's isentropic. Same entropy all the time. You know the volume because it's the smaller volume now. And then you now know the pressure because you just solved for it now. Now that you've done that, now you have your heat addition. So that's your heat addition. What you can do is you can also solve for U. Either lowercase u or uppercase u. I forgot which one it is, but you're solving for the heat or the energy. So probably H is probably a better value for this. Yeah. What you can do is you can calculate the temperature at B, the temperature at C, and then use CP values. So if you have a particular heat addition, you know that U is equal to CP delta T. Yeah. Oh, in our case, you'll be using CV. So CV was H. H is equal to CV delta T. My bad. And this is your heat addition when you add stuff in. You have a particular hot or cold value. So you can look this up for this particular pressure or temperature, or this temperature range or something like that. Once you know your pressure as well, you can also get temperature as well. So once you have these, you can directly solve for one another. You can look them up in tables and they should be able to like pop out to you, or you can like linearly interpolate. There are like websites that can linearly interpolate for you as well. So you can just chuck in values and they'll get it for you. Anyway, so yeah, you have your CV, you have the change in temperature. The way you could do that is they'll probably tell you the maximum temperature. If they don't, they'll probably tell you the heat input. So either they'll tell you the change in this enthalpy, or they'll tell you the change in temperature. Based off that, you can solve for the other one, whichever you need. Normally, I think you work off and you get the change in temperature. With that change in temperature, you can find the state at that, because now the volume is the same and the temperatures, like the new temperature is known. So then you can solve for the new S. New S value, which is the entropy at point C. So it's like kind of like a point-to-point sort of thing, if that sort of makes sense.
Yeah.
Did that actually give you any information about the heat addition, about maybe the fuel burning or something like that?
I'll have to check. Give you volume and pressure.
Sorry, what?
For the engine data, they give you volume and pressure. I think that's what.
You probably then go with the highest volume and highest pressure top. So the maximum pressure at the minimum volume, or something like that.
Yeah.
Does that sort of make sense? You can just use that maximum value and go off.
Oh yeah.
Yeah. So either
Yeah.
way, you still need to solve for this SC business. So maybe you can use this. If you don't need to, then just go off the pressure. Either way, you just need the pressure at C, and then solve for the entropy. Once you know the entropy at C, then you automatically know the entropy at D, and then you just have a different volume.
Yeah.
And so SD is now equal to SC, and so you basically now know this one. And so all you're looking for now is the volume as well, because that's going to be the BTT, the maximum volume, and then from there you can get your temperature or your pressure as well, because these both can be read from your tables as well. I think the way your tables are formatted is it'll tell you like temperature, pressure, and then it'll tell you S. It will also tell you H or stuff like that. Normally you'd be working with S, because here it's either the volume that's constant or S is constant. So you can work your way through with that. Does that make sense?
Yeah.
That's actually like, okay, hopefully that actually explains things well for you, but yeah. And then so now once you know D, then you can just drop down back to A, and you already know where A is. So you can draw yourself your nice complete cycle. And yeah, that's that. Yeah, so once you know your full thing, then you can calculate the energy. For example, the energy of the whole thing is your heat in minus heat out, and then like you can work your way through with that. So you can take the enthalpy at D, H at D. You can work that out from the table as well. And then you can just take the change in energy, or the work really. The work of the whole cycle is going to be like the heat input, the amount that went from B, C. So I can say HB, HC minus HB. And then that whole thing, that's the input. And then your output here is going to be H, D minus H, how much you exhausted. Did that sort of make sense?
Yeah.
That's basically the Otto cycle in its entirety. You should be able to get everything else from that. And any piece of information that you don't know, because you have enough information about every state, you can just automatically solve for anything else. If you want like the lowercase u, if you want to know, I don't know what else you need to know, you can work it through from there. Alternatively, if you want to know, like say, for example, the mass of the air, you can assume ideal gas at standard pressure, like at atmospheric, and then like volume, and then work out the mass as well of the air if you really need to. Highly doubt, big doubt, but if you do, in case, I don't know.
Yeah.
Okay. So that's the Otto cycle in a nutshell. After that, you have your diesel cycle. the diesel cycle works in a very similar fashion, except that there's different things that are constant. Okay, so basically from there, instead of assuming that the entropy is constant that same way, or that the volume stays a constant up here, instead of that, what you assume is kind of like a, I don't know, like a weird like quarter annular sort of thing. It kind of looks like this, and this is the pressure volume. So the way you're thinking about this is the same initial point, or I'll call this point A, works in exactly the same way. So this is where you start off. This is like ambient. Ambient, and then this is your T, sorry, BDC, like your maximum volume. Yeah, that's your maximum volume. When you go all the way up to point B over here, this is now S equals const. From across here, as you can see, the pressure is now constant. So there's a slight difference. The difference here was that before here, the volume was constant. Down over here, the pressure is constant. Does that make sense?
Yeah, yeah.
This is, yeah, so that's over here. We have, this is where the heat input goes in, by the way. When you add heat, instead of increasing volume, or increase pressure, you increase volume. So that's, sorry, P equals constant. And then from here, you can work it practically the same way. So it's kind of, again, just trying to link things one at a time. So from here, you want to know what S is, because that tells you, S over there. You know the volume at B over there. And because you know both S and B, S and volume, you can triangulate everything else from that, if that sort of makes sense.
Yeah.
Yeah. And the tables will be able to give you everything once you know 2 pieces of information. That's the way most of these tables work.
Right.
Yeah. So now from here, you know what S is, and because of that, you also know the volume and you know the pressure. Once you know the pressure at this point, you also know the pressure at this point. Once you know the pressure at this point, you need to know the volume. So you don't know what this volume is. But you can figure that out. There was a way to work that out. The way you want to work that out is through your cutoff ratio, I think. Yes, it's your RC sort of thing. Yeah. So so the way they noted this was V3, and they noted this is V2 because this is like part 2 sort of. But RC is the cutoff ratio, which is basically how much more volume is this than this. So in our case, like in our context, the cutoff ratio is going to be VC over V. Once you know this ratio, then you can calculate and multiply it. Does that make sense?
Yeah.
So this is your maximum volume, that's your minimum volume, and then how much bigger is this volume than the minimum? And once you know this volume, then you can again apply that. You calculate the entropy at that point, and then from there you'd work your way through with the maximum volume again, and then calculate what pressure you're at.
Yeah. Yeah, that makes sense. Yeah.
Okay. Hopefully that explains and clears things up. The work again in our case is going to be the energy at C minus the energy at B minus the energy at D minus the energy. So that's your heat in minus heat out. That's quite literally it. Heat in minus heat out. That's probably why you need to know your temperatures. So the way you can work that is H is equal to MC. I think it was the pressure one, or was it the volume? I think it was volume. Volume, pressure. Oh, yeah, I think it's the pressure. Yeah, CP. CP delta T. So once you know the change in temperature, you can get the change in H. You can calculate the H value at the start as well, and then you can find like the temperatures at each of those, or like work your way through. Or like this is a weird approximation because you meant to M delta H. You can find H at each of these values, and then you can work it through as well. So you can get all the information you could possibly need once you know all the four states. At least if you have two pieces of information, you can work everything else out from there because you just read off the table.
Yeah. Okay.
Yeah.
Yeah.
Hopefully that makes more sense.
Yeah.
Yes. No. Maybe. I don't know.
When drawing these like graphs, like how would you get like the curved part, like
the curved part? So it's not actually finding anything that's in between. All you're really worried about is the start point and the end point.
Okay.
The exact equation of the curve, that's not like relevant to you at all.
Okay.
Or you know, it could be like a weird squiggly line. Who knows?
Yeah.
So it's not of concern. So that's the diesel cycle there, and then on top of that you have the dual cycle. So the dual cycle is kind of like a weird amalgamation of the diesel and the Otto cycle, in the sense that the Otto cycle had a vertical over here, the diesel cycle had a horizontal. So the dual cycle would be like, why not both? You know, that ad. I don't know if you know which ad I'm talking about.
Yeah.
You know, the one like taco ad or something, the Mexican ad. Never mind. Like, why not both? And then they will chill. Never mind. I guess I'm done for saying this now.
I don't know that.
All good. So let's just like continue on. Why don't we? So yeah, you start off at your ambient once again. So this is your maximum volume. I'll call this V max at this point. And then this is your minimum volume. So from here, once again, S equals constant. You end up at this point, across with your minimum volume. And so you know this at point B. From here, you're going to have a heat addition at like kind of both of these, if you can sort of see what I mean. There was a way to do this. So the way that you want to do this is, okay, so your cutoff ratio is, your cutoff ratio once again will be given. And that's going to be, I'll call this V, so that's X and I'll call it C. So it's going to be VC over, you can say VB or VX because they're the same volume, doesn't really matter. That's the same thing as VC over VX because VX is the same thing as pressure and this is volume. Yeah, since they're the same volume there. So, you know, yes, no, yes. Hopefully that makes sense. Yes. Okay. So that's that with that over there. Once you know what VC is, what you can do is, let's see. There was a way to work this through. How do we work this through? You also had this RP value, I think. And that basically tells you your pressure max over this pressure PV. Normally, like in lectures and stuff, they number them 1, 2, 3, and 4. But I did A, B, and C, and D. It doesn't matter. The meaning is what is important. Just don't use the same notation as me, otherwise they may get confused. And so once you know this pressure ratio, this is the max, P max. So the idea is that, remember, like your cutoff ratio is like kind of telling you how far this is. This pressure ratio tells you how high this is. Does that make sense?
Yeah.
Okay, that should clear things up. And then yeah, from there you work your way all the way around and then work your way down. Hopefully this sort of makes sense. Again, every point you have two pieces of information. Here you have volume, Vmax, and your entropy, that's your initial amount. And you know that because you know your pressure. If you know pressure and volume, you can know your entropy, read it off the table. From there, you know so the only thing that's changed at this point is the volume. And so the pressure necessarily will change. Oh, I need my I need my laptop charger.
Okay.
Thanks. Anyway, so that's beside the point. Yes, so once you know how high this is and how far across this is, from these ratios, you're able to know the states at all of those points and then work your way back down because you know the state, which is S over here, down. That sort of makes sense. Hopefully I didn't yabber on too much.
Yeah, that really helped. So it just
Really so.
yeah, go like points and then draw them together.
Okay.
I don't know if they expect us
it's all coming
like,
together.
I don't know if they expect us to generate it on MATLAB though.
Probably not generate the plots on MATLAB per se. Not necessarily generate this. Maybe.
I have to check.
Yeah. So that was that. The plot may or may not be like able to be generated on MATLAB, but yeah. It's probably going to be pretty hard to make this on MATLAB, but
Yeah, so I was
how
thinking.
you do that actually. Yeah. Let's see.
Because I remember them saying that like charts have to be made using MATLAB or Excel, but I'm not sure if that like applies to like the cycles. I might have to ask on Ed. Yeah.
Oh, this is also a pretty important point as well. This is like a general tip that they kind of said. So there's two general tips that they said for cycle analysis. Number one, so tips. Okay, so number one, mass is always constant. This is a closed system the entire way through. And so if you know the mass at the first state, you know the mass at every state. The mass doesn't exactly help you calculate any of the other stuff. So was it PV equals MRT? You know this guy.
Yeah.
The other thing that you can use this kind of information because you can use the combined gas equation. And so you could have P1 V1, T1, P2, V2, T2. This generally tends to help you bypass a lot of things. This can only be used where S is constant from memory. I don't think you can use them. Let me make sure of that, but I'm pretty sure. Or can you use it all the time? I forgot if you can use it all the time or not. I think you can use it all the time. Maybe, I think. Seems reasonable. I think you can. Because the idea is if you can rearrange this, PV on T is equal to M times R. M is a constant, R is a constant. So the overall idea is that PV on T will always be a constant because it's basically a measure of the mass. And since the mass stays the same, then they should actually hold. So you're always able to solve for the volumes and temperatures if you need it. You know the volumes, maximum and minimum, and you also know VC. So you can just plug, chug, and you can get all the pressures that you need.